So we've been doing variational inference today. Let's get our heads back into Gaussian processes just for a second, remind us of what we were doing on Tuesday. The goal with a zero-mean univariate Gaussian process is we're trying to describe all the dependence relations between all of the various data points sampled from some target series. And you, of course, constrain that to some sort of kernel parameter, some sort of kernel form that we talked about a lot on Tuesday. I won't focus so much on the various forms. But the idea is still you're constructing a matrix that captures all the dependence relations between those points. Now, in the real world, we never have noiseless observations. So an observation model on the Gaussian process can be expressed as such for a scalar target series, where I've also included these functions h as explicit basis to describe drift in the process. Previously, we referred to them as the mean of the Gaussian process, but without loss of generality, you can take a zero mean and just absorb it into there. And critically, you always assume that there's independent observation noise over the data samples. Now, extending this to multi-output processes and taking our time a little more to fully understand them, in this example, we have a two-dimensional output. In general, you could have n dimensions. But now the goal is not just to capture the autocorrelations within a single series, within all the points along a single series, but also the relations between a single point on the different series and the cross-correlational behavior between all of the data points across all of the different series. This isn't too hard to extend because this really just gives us a new kernel matrix that has a blockwise form. And all the diagonal blocks of this matrix are exactly what we were dealing with previously, and they're what we would get if we just fit individual univariate Gaussian processes to each individual response. But the key idea is in a multi-output model, we're now fitting all of these lovely off-diagonal cross-correlation terms. And that's going to give us a lot more analytical or computational and predictive power, as we'll see later on. So this is easiest to extend analytically or notationally if we talk about a particular data index I. Now, it's the entire index that is itself a multivariate normal. Again, defined with an explicit basis function that captures drift, and we have our now multivariate, multi-output Gaussian process there. And I am going to, yet again, simplify by assuming not only do we have independent observations over the data, we have independent observations over the target responses. And again, the point is now this big, larger kernel matrix K now captures cross-correlations between the multiple response series. Okay, going back to learning the parameters, a slight extension of what we did on Tuesday is now considering doing a regression weighting scheme on the explicit basis functions. One of the easiest ways of maximizing our posterior distribution is to analytically find the conditional optimal estimate for the weight matrix over those explicit basis functions as follows. And then you can numerically optimize that using the gradient methods we discussed on Tuesday to find optimal set of kernel parameters and the observational noise in the model. And I spent a lot of time on Tuesday talking about how, yes, this gives you a numerically precise estimate, but it requires inversion of what was previously an m by m kernel matrix. Now I'm making it even worse. I'm saying it's n times m by n times m, where n is the number of target responses. So you can imagine if you have like 500 data points for 3 different series, now you're inverting a 1500 by 1500 matrix. A lot more expensive than it was before when you were just considering univariate processes. And so this takes us into sparse Gaussian approximation schemes for learning the parameters for Gaussian processes. And there are countless subtypes of algorithms and methods here. I'm not going to go over the super specific ones, but in general, they're always based off of the idea of using a subset of the data we'll refer to as inducing points or an active set. And we'll consider that to have cardinality L, where L eventually will assume it's much less than the total number of data points that you have. And the whole idea with these sort of schemes is always to approximate the true kernel matrix with a low-rank decomposition that only involves the inversion over your choice of inducing points, over your active set, which by construction is going to be smaller than the total number of data points. And thus, this improves our computational time by a significant degree, assuming that L is much less than M. And going back to the learning scheme, we can now define a subset regression optimal estimator, where we simply replace the true kernel matrix with our new estimate. And by the magic of the Woodbury identity, the inversion stage in that parameter learning is now done much more quickly, because we only have to deal with inversion of an n times L by n times L. Of course, this is called an approximation for good reason, because whatever we gain in computational time reduction, we lose in numerical accuracy. The more, if you consider the fraction L over M, the further away that is from 1, you can imagine the much more inaccurate your approximation is going to be at the end of the day. And if that's not enough for you, we can do the variational approaches that we were talking about today. And I'm skipping a ton of steps here because I probably would not have time or space on the slides to fit all of them. But if we talk about minimizing the KL divergence against a zero mean Gaussian to try to estimate our kernel, then these lovely people have already done all the work for that particular approach. And you can define a stochastic gradient descent scheme as follows, where you can iteratively estimate the stand-in for the low-rank kernel matrix. And the additional factor that really speeds up computation in this scheme is the fact that we've also linearized or factorized over the input dimensionality from our data. You can couple this with mini-batch persistency, multiple epochs, whatever your favorite stochastic gradient method happens to be. And we've now reduced the computational time down to PL squared for a mini-batch of size P, which they do sometimes mention P should be greater than L, but it can certainly be less than. But let me just say, I tried for several days to get these methods to work on different types of data, different types of systems of multi-output processes, and it takes a lot of tweaking. It's a very touchy process with respect to your hyperparameters like learning rate and mini-batch size, so on and so forth. So its generalizability can be a little bit limited. Okay, so let's talk a bit now about the benefits. Why would we really want to use multi-output Gaussian processes for regression? In lieu, because we just talked about how computationally expensive they are, but numerically they offer us a lot of benefits. And if it's a little hard to see in this figure, we'll see a slightly better one in a bit. But the one you should really pay attention to is the mean squared error of our regression, as opposed to the univariate fits on the left and a joint multivariate model on the right. You can see the multivariate MSE is reliably way less than what you get from doing individual univariate models. Because, in a sense, the multivariate model is pooling all of that data and using it for estimating each individual series. Now you might say, okay, that's just higher accuracy on a training set. Maybe we're just overfitting the model, but it actually does an even better job for forecasting and prediction as well. If we consider a situation where we train using either 30% of the data or 70% of the data, and then we try to generate forward predictions or forecasts up to some point in time, the multivariate model provides much more stable estimates over a long period of time, the further away we get from known locations of data. The univariate model can do a little bit better sometimes for very, very short step ahead lags. But by and large, the multivariate model does a much better job for forecasting. And the really interesting property that actually caught my eye when I was looking at projects is their reconstructive ability. If you imagine a situation here, and this plot has a lot of interesting stuff that we can look at. But if you imagine a situation where you have these target series and then I randomly delete entire blocks of data inside these green regions, ask what happens if I fit univariate models on the left and a joint multivariate model on the right. One of the first things you'll notice, even if you look outside of the green regions, is you'll notice the confidence intervals on the univariate processes are quite large. They're quite fat, and they don't quite capture the true noise of the series, whereas in the multivariate model, at least in the regions where data is dense, the confidence intervals are much, much thinner, reflecting the higher accuracy in the actual mean prediction. But of course, the big interesting thing about this is what happens within those green regions where you can see very clearly the univariate processes freak out. They don't know what to do when they see this block of missing data. They immediately create the usual cusp inflation in the confidence intervals that we've come to expect from Gaussian processes, but they don't do anything clever with the mean prediction. They literally just splice the two, they just provide a linear splice between the most recently observed points in that series. Whereas if you contrast that with what the multivariate model does, well, it not only reconstructs the curvature, but think about how it does that. It does that because it's correlated all these different target response series. And in these other series, you didn't have missing data in that interval, so it's taking the observations from the other two series and using those to reconstruct a best guess of what happens when the data is missing. That does have a drawback, if you'll notice, because now in the regions where you don't have missing data on the other two series, you do see a slight inflation of the confidence interval. You do see some slight variation of the mean prediction as well. So there's a little bit of a trade-off there. What you gain in reconstructive power in the region of totally missing data, you lose in the other regions, where if you compare that to the univariate model, it did a fine job everywhere it had data. I think that just about uses up all my points that I had for that. All code for generating the figures and model fitting for this was done using the GPMAP repository, not GPML, available through the website of Neil Lawrence at the University of Sheffield. The website is inverseprobability.com/software. Lovely package. The documentation is a little sparse, but if you spend a couple of days looking through the code, really come to understand everything that's going on, it's very nicely generalized and applicable to just about anything you'd ever want. So thanks for listening. Are there any questions? Yes.
Yeah, so I was curious, you mentioned that with this multi-output GPs that they're pretty sensitive to training. I'm also
That was the variational.
Oh, okay.
That was a variational approach.
So,
the exact learning always works, but is very slow.
Yes.
The subset approximation generally works pretty well. Just use a somewhat large number of inducing points.
Yeah, I was just curious if you saw, like, comparing just like, you know, your regular GP versus this multi-output one, like how exactly the training differed between them, or were they pretty much trained about the same?
Well, the
Like
multi-output always takes longer to.
Okay.
It always takes longer to train, necessarily, because you're learning all of those additional off-diagonal blocks. Now, I never really looked at too many target response series, but you can imagine for 3 target responses, for 3 multi-outputs, you're only training 1, 2, 3, 4, 5, 6 additional blocks. So it's not going to be too bad. It'll necessarily be worse, but not too bad. But you can imagine fitting 100 processes over even like 10 data points. But now there's a huge difference between fitting 100 different univariate models, basically all the diagonal terms, and then fitting the joint multivariate model, which will be massive. But again, that's where the subset approximation comes in. Oh, and something I did forgot to mention, when you do the multi-output subset regression with active sets, you do have to assume that you're using the same inducing points for all the series. I tried thinking maybe if that was a necessary condition, that maybe you could use a different active set for every target response. Turns out you definitely need the same inducing points for every single target series in order to capture the correlations. Otherwise, you're never really getting a true picture of what the cross-correlational activity is. Any other questions? Yes?
For the last one, two slides that you trained, you said that the multinomial Gaussian feels better for the interval of gaps of the missing data. So I wonder, have you tried other data sets, other data sets, not this data set? Because in this data set, it looks that it's a sine of sine function.
Yeah, so something I didn't mention is what this is generated from. This is a sine function, this is a negative sine function, this is a period shifted sine function. So those are very nicely stationary related, highly correlated series. I did try it on a couple other examples, in particular a Lorentz system, which is highly non-stationary, highly non-predictable over various regions. And what it really comes down to is you can remove data from various regions, but you do need lots of samples from regions of similar nonlinearities. So if you have an aperiodic irregular type of signal, you need multiple repetitions. You need more data, basically, to deliver a same quality, to lead to this sort of replication. Basically. Is that?
In other non-periodical data set, does the multinomial Gaussian processing still better than the invariant Gaussian processing?
I didn't have time to test that. Something I'm going to do over the weekend actually is related to OU kernels, because those are more directly related to time series analysis. But I suspect it will. I suspect it will, especially for a times zero